This week, the presentation is on ensemble methods. Let's start with some basics on ensemble. So first thing, there is the no free lunch theorem, which is a theoretical notion that no learning algorithms is superior to others for every problem. This is rather theoretical in the sense that we are considering the range of all possible problems, including problems that are pure noise or totally decorrelated between each other in terms of near samples, which is, of course, not common in real life, in nature. In nature, there is some regularities, but if we just consider the space of all possible problems and we integrate over that, we can show that there are no specific learning algorithms that are better than the others. Of course, for real life, we have some patterns, some I would say regularities in the data that can be used for learning something. But the point is here that we cannot consider that there is one single perfect, or I would say best learning algorithms that we can use for every cases. I mean, every cases require different algorithms, and possibly many different algorithms can give different, I would say, decisions, but in the end being about to be comparable in terms of performance. So the idea is to say, let's maybe build many of those. Let's try to learn over different algorithms with different configurations to build an ensemble, and then let's average over that. And because the notion of averaging is important, we can say that for a single sample, here a sample is a training of a model over a set of data. You can say that we can be lucky or unlucky. That model that is trained may lead to poor, or I would say outstandingly good decisions for the training sets, may not necessarily generalize well. So if we average over a set of samples, we can build an ensemble of many, I would say, diverse and reasonably well-performing models. And if we average a decision, we can get even better decisions because we will be less likely be, I would say, put in a decision. We will be not rely only on one case, one model that may make mistakes in some cases. Averaging will allow to average over different decisions and take the one that is possibly not an outlier decisions, being more aligned with what we should expect with that data to classify, for example. And as such, I'm relying on averaging over ensemble decisions will allow to remove or at least reduce the variance on the decisions, which is a really good thing because some of the variance may be just the fact that for some cases there are many possible decisions that different models will take. And we tend to possibly fall on the most common decision by averaging over many decisions from ensemble models. And as such, it removes noise from individual classifier decisions that can be noisy, that can be just wrong, plain wrong in some cases. So, and not necessarily coherent with the other decisions from other models from the same ensemble. A common sense explanation for that is that several heads are better than one. So more concretely for the presentation, here we will talk about approaches like voting methods, where we will take many models that will vote about the decision to take for a given sample, dataset sample. We can also rely on error correcting output code, which is a common approach in digital communication that is applied in the decision function for ensemble, such that we get more models than required, and we allow some of those models to be wrong. And as such, the error correcting output codes will allow to still take good decision according to the majority of models in the ensemble, tolerating some errors. We also have the notion of building dynamically datasets and features used to train individual members of the ensemble, which consists of many different approaches that we will detail later. And there is the notion of mixture of experts, where then we try to build an ensemble where each member are specialized on some aspect of the problem, generally some region of the input space. And we want to get those members to be experts on their specific regions. And as such, when we have data to classify, we will weight differently the different members of the ensemble according more weight to the experts for that specific data sample. Let's go back to something quite fundamental about the Condorcet's jury theorem. And this theorem allow us to look at the probability that a jury will get a majority decision that is correct, assuming that there are two possible decisions, correct decision or wrong decision. So each jury has a probability P of making a correct decision. So it has a probability P. And as such, if we figure out that the probability is the same for all jury members, and if the probability is more than 50%, 1/2, the probability of correct jury global decision tends to 1 with a very large number of jury participants. So with large jury, where each individual members are making a better than luck decision, the committee will make the right decision if it is large enough. Conversely, if the probability is less than 50%, then the probability of a correct decision goes to 0 as the size increases. But I mean, we expect that each member are better than luck and making, I would say, an informed decision based that is, in fact, the decision can only be correct or wrong. There are no other options. And we assume in that case that the votes are independent and identically distributed, ID. This is an important hypothesis. It assumes that the members are not necessarily influenced by the same points. They are making mistakes, but not the same mistakes for the same data sample. The mistakes are distributed such that the decisions are independent, but having the same distribution overall. That has been proposed by the Marquis of Condorcet, de Condorcet in 1785, just before the French Revolution. So this is somehow a mathematical justification of democracy that is studied in political science. It really brings up the point that making decisions based on juries, on committees, should lead to more robust decisions, better decisions compared to having single individual. And as such, the extreme case is to use the whole population to make a decision to choose, for example, representatives, and that choice should be the best one to make, theoretically speaking, because of course, the notion of independence between the people participating to the vote is really strong. So there are different, we can build ensemble in different ways. One approach may be to use different learning algorithms. As such, it means that these different models have different assumptions about the data, different bias, different variance. So, and then you can mix, I would say, a k-nearest neighbor with a multilinear perceptron, with SVM and so on. So we can really build an ensemble of different models. This is conceptually appealing. This is not something we do in practice because it requires to be able to make all these different algorithms to work correctly, being correctly configured for a given data set, which is not necessarily an easy task. We often go rather with the idea of using one model, but possibly with different hyperparameters, like for with layer perceptron having different in the number of neurons, layers, neighbors, different covariance metrics. So this is, I would say, easier to do because we can focus on one model and change the hyperparameters. But even then, this is not necessarily the most common approach. I would say it's not that common, even though it's something that can be done. Then we can go with using different representations of the data. So if we assume that we've got different modalities input from different sensors, different measurements, we can split these measurements over different models, and each model doesn't have necessarily the full view. It has a sub view or specific elements as input for making their decision. Or I would say there's even the notion of just sampling the features. If we see the features are already put in a vector of a given size, we just make a subset selection or subset sampling of these features to train models. And so every model has a different subset of samples. This is quite commonly done, for example, in random forests and random subspaces, where we will make use of this point of building members with different subset of features. There is also the notion of having different training data sets. So, for example, bagging is basically relying on that. We are making random sampling of data with the possibility of drawing several times the same sample. This is one approach. We can also guide the sampling according to the misclassified data. This is the core idea with boosting. So we need to take into account the complexity of basic classifiers. So the idea is that with an ensemble, we don't have to be very precise with the individual samples, with individual models. We need, in fact, to prefer simplicity over performance, because the point is not to get individual models that are super precise, super well performing. We prefer diversity, so we rather aim to build an ensemble of simple models that are diversified, that are not making the same mistake on the same data. We could get them to be specialized, or we could get them to be trained on different subsets in different ways. The point is that we don't want them to make the same mistake on the same sample. We want them to have a diverse profile in terms of decisions, and as such being trained in ways that enforce that diversity over the basic members making ensemble. And as such, if the classifier's errors are RID, which again, it is quite a strong hypothesis, but let's assume it is possible to get these errors to be, I would say, evenly distributed over the sample, then as such, with a data set that is coming close to infinite size, the decision of the ensemble with each individual members are making IED errors, is getting about to be the Bayesian error rate, optimal Bayesian error rate. So basically, we cannot beat that. It's really like the best score we can expect with a classifier over a data set. So there are different approaches for combinations. We have this idea of having multiple experts working in parallel. This is quite common, like when we get into votes, including weighted vote, a mixture of experts. Stack generalization, we will not see it here, but that's another approach where we can work in parallel. While we can get also a multi-stage approach in series, which is much less common, but something that can be used, for example, with a cascade of classifier, where we'll see one case that is particularly interesting for real-time processing, but otherwise it's not that common and not necessarily that useful out of the idea of real-time processing. In fact, the formalization of ensemble methods is that we have a meta classifier that we will call H bar. So H bar here is really the model of the ensemble that includes a kind of gating function that is integrating all decisions for individual members, and that is providing the H bar, and H1, H2, HL are each individual member decisions. So basically, we have individual models that are making a meta model, the ensemble, and the meta model by itself can be seen as another model based on the individual decisions.